Hey folks, welcome. Today is April 21st. This is my second. I spent about an hour building this video once already. Interacted with the document camera, showed you some actual examples of reflection and refraction. And then when I went to save, the whole thing just said, no, errors, we can't do it. So I'm going to break this into two videos. I'll do the slideshow first, and then I'll do a little bit of demo on the document camera. Again, the picture's not fantastic, doesn't translate great. I might try a different camera tomorrow where I actually try and take some measurements off of the examples of the refraction that's going on with the lasers. So we'll see that a little bit later, but today we're going to talk about introduce reflection and refraction. We're not going to do the quantitative, the problem solving from section 5.3 of the workbook yet. We'll get to that tomorrow and maybe even into the next day. So reflection and refraction. So here we've got a incoming light ray. This represents white light. It's got all the colors, the Roy G. Biv. When we're going to look at it, we'll always use monochromatic, because what would actually happen here is there would be a spreading, a dispersion, and you would actually get, with refraction, you'd get a rainbow. So you wouldn't get a clear pinpoint. You'd get a range of places. So we'll use monochromatic. Today I'm going to use a violet colored laser, and tomorrow probably a green. So incoming light, incoming ray, incident ray, and then it's going to reflect off the water. And we've seen that, of course, many, many times before. We're going to find out a little bit about the properties of that reflection. But some of the light will actually go into this more dense medium of water. So going from a less dense to a more dense. And in this case, you can't see it very well here, but the light is actually bent a little bit downwards. We'll look at that in a bit. Hits the bottom, reflects off the bottom, gets to the top. Some would escape, perhaps, but if the angle is right at the critical angle, it's going to refract back down. We call this total internal refraction. So the light will bounce down in and out several times before it actually gets up. Has a couple of effects. One is that it warms the water, kind of the greenhouse effect going on there, but also it makes the water spark. Excuse that cough, not a COVID cough, as our bosses say when they're on the phone. All right, so moving on. So here we have the incident wave. So this is represented like a water wave coming in. These are each of the wave fronts. They come in, they hit the shore or a surface or a dock or a break wall, and then they bounce out. That bouncing of a wave off of the surface we normally refer to as reflection, when it's any kind of wave, whether it's water waves, sound waves, or what we're interested in here, EMR, light waves. So a couple of really important standards and definitions. First of all, the normal. The normal, when we have the surface down here, the normal is an imaginary line that comes off that surface at 90 degrees. And it's from that normal that we measure the incoming angle, which we're going to call the angle of incidence, and the outgoing angle, which we're going to call the angle of reflection when it is reflection. So it's very important we don't measure that angle against the surface. And if any of you get some questions wrong on upcoming assessment, it's because I'll tell you this is a 60-degree angle, but the angle of incidence then is a 30-degree, right? Or I'll tell you this is a 40-degree, and then that means the angle of reflection is a 50 degrees. So this and this, of course, complement each other to form a 90. But we always measure against the normal, not against the surface. Why did they start doing that? Because of irregular shape on the surface itself. So that angle can be different if it suddenly has a slight slope going down here than what we're going to follow the properties of. So let's look at something called the law of reflection. Again, when we measure the angle of incidence from the normal and the angle of reflection from the normal, what we know to be true is this, that the angle of incidence equals the angle of reflection. So if this is a 30-degree incoming angle, incident angle, the reflected angle is also 30 degrees. If this is 40, this is also 40. If this is 20, this is also 20. So whatever the incoming angle when measured against the normal is, the outgoing, the reflected angle is the same. And that's your law of reflection. And again, this is going to tell you both angles have to be measured, not from the surface, from the normal. So let's jump in a little bit into refraction. So refraction is a property of waves where they bend when they change medium. So refraction is the bending of a wave due to a change in the density of the medium. Now, EMR, light waves, they bend differently than other kinds of waves. So when light goes from a less dense to a more dense, it bends a little bit differently than the other waves will. And they slow down, whereas other waves will speed up and are more dense. Wavelength, speed, and the angle of orientation all change. So when it comes to these properties of the wave, specifically we're talking about light, its wavelength, its speed, and its angle of orientation are all going to change. But one thing stays the same. Another question coming up on assessment, and that's frequency. Frequency will remain constant. So even though the wavelength and the speed change, remember that universal wave equation, V equals F times lambda, ties together the speed, the frequency, and the wavelength. These two are going to change, but this will always be constant. Anytime you take the speed and divide by the wavelength, you'll get the same number of frequency. So these are going to change proportionately to each other, and then also in proportional to the angle of orientation. So let's take a look at some actual examples of refraction. So here we're going from glass, is the starting going into air. So going from glass into air. So this will be theta I and this will be theta R. So this would be theta 1 because this is where it's coming from. This is going to be theta 2. This is going to be the medium 1. So it'll be N1. This will be N2. We'll see how that comes up in a little bit. But look what happens. So what I've drawn here is the incoming ray, and then I've got this green ray is where it would have went if it didn't bend. So you notice what's happened. The refracted angle, the angle of refraction, is larger than the angle of incidence. So it bends away from the normal. So when we go from a more dense to a less dense, it bends away from the normal. So we have a little bit of a mnemonic. I have a mnemonic device I like to use for this, MLA. And this is how I always remember it. Because I know who the MLAs are. Those are those fine gentlemen who get elected across the province, and then they go to Edmonton and they represent us in the Legislative Assembly for the province of Alberta and make some laws, make some decisions, and spend some money on a whole bunch of good things. And those MLAs. Well, MLA here stands for from more to less dense medium. It bends away from the normal, and that's what you can see here. So because it went from glass to air, which is a more dense to a less dense, the light's going to bend away from the normal. Consequently, the angle of refraction is going to be greater than the angle of incidence. Let's look at when it's the opposite. So now we're going from a less dense, air, to a more dense, water. Our letters for that are going to be LMT, and I don't have a mnemonic for this, but it's just the opposite of MLA. So instead of ML, it goes LM, less to more. Instead of away, it's going to go towards the normal. So you can see that happens. Here's your incident ray. Here's where it would have went if it didn't bend, but it bent towards the normal. Consequently, the angle of refraction is less than the angle of incidence. Theta I will be a smaller number than theta R. Okay, so MLA, more to less away, LMT, less to more towards the normal. So let's take a little look here at some 3 different mediums. So in each case, we're going to start at air, and we're going to go to a more dense medium. So air to water, then air to glass, and glass is more dense than water. Then the third example goes from air to diamond, and diamond is more dense than glass. So we're going from less to more, so it bent towards the normal. Hard to see in this diagram, but you can see this was 45 degrees, this is only 32. It bent towards the normal. When you go from air to glass, you can see it's more pronounced. It bent even more towards the normal. And then when you go to something very, very dense like diamond, it's going to go down to 17 degrees. So the more dense it is, the more it's going to bend towards normal. So they use that relationship between air and the density to come up with an index of these values. So they started with a vacuum, and they're going to start with a vacuum, the vacuum being equal to 1.00. Air to 3 sig digs are still going to be 1.00. And then using those angles and the relationships and the proportion of the bending, they came up with a whole series of indexes. So when it comes to refraction of light, they follow Snell's law. So this is the way Snell's law used to be listed in the formula sheet, the data book from Alberta Ed. So it shows the angle 1 over angle 2. This, generally speaking, is the incoming angle, and that's the outcoming angle. So that's the way. N2 will be the index of refraction for the second, what it's going into, over the first. The speed at the first over the speed of the second, wavelength of the first over the wavelength of the second. Now, if one of these is error, we're going to know the speed is 3.00 times 10 to the 8 meters per second. So that's going to be a key for answering some problems as well. But this is the way it used to be listed. It's not listed this way anymore. Now they've gone to this format. So on your formula sheet that you guys are carrying at home, this is the way that Snell's law is going to be presented for you. So it's got the n's and the thetas, and then the n's, the v's, and the lambdas. Now something important, you notice that n here it's 2 over 1. It's 2 over 1. The other things, the angles, will be 1 over 2, 1 over 2, 1 over 2. So the n's are always the opposite of everything else. You're not going to use all parts of these. You're going to use just 2 things at a time. So n and theta, or n and v, or n and wavelength, or v and wavelength. Or you could use, sine theta. You can go back to the original form here. Okay, so you notice the ones. Now, I'm going to show you, demonstrate this, where you're always going to put up in the upper left-hand corner what you're trying to find. So you might have sine theta 2 over sine theta 1. And then you'll use the secondary. But remember that if you flip one side, you have to flip the other side. So instead, if this was sine theta 2 over 1, it'd be n 1 over 2. Or it'd be v 2 over 1. Or lambda 2 over 1. We'll see that tomorrow when we start answering some questions. So a little more about this n then. So this was how they found it. So they would take n1 for air. They would take an incoming angle. They would measure the outcoming angle, much which we're going to try and demonstrate for you a little bit today. And then we'll do specific examples tomorrow with our rectangular prism and our lasers. And then they can find what the second one was, and so on. So when they did a series of those, they came up with a table that kind of looks like this. So in a vacuum, that was our standard. That was where we started. Air to 4 sig digs are still going to all be the same, 1.000. But because air is a little more dense than a vacuum, air actually does have a slightly larger index of refraction. I don't think, unless maybe Kennedy Oswald in the workbook might have thrown a question where they're going to give you more data than that. Water, 1.333. Ice. Now, ice is just frozen water. So why is it 1.31? Well, we know that as water freezes, it actually takes in air and it expands. It's the only substance that expands when it freezes. Absorbs some air because there's more air in it. It does have a less density, so it's going to have an index of refraction a little bit less than liquid water. Glass, about 1.5. The reason they do that is because there's lots of different kinds of glass. We'll see that in the workbook. Table, similar to this, but a little bit different, is in the back appendix of the workbook as well. And as you work through the workbook problems, you'll be expected to go back there for it. Of course, when I do my demos, I'll cut and paste them right onto the Smart Notebook for us. A diamond, quite a bit more dense, 2.417, 2.42 to 3 sig digs. All right. So again, this is just a little summary chart from that first page. You've got incoming. Some of it, the light, is going to be reflected. The angle of incidence measured against that normal is equal to the angle of reflection. That's the law of reflection. But some of the light's going to go through and bend. In this case, we're going from air less to a more MLT, so it bent downwards more towards the normal. Hits the bottom, it's going to reflect and follow the law of reflection. When it gets up here, what happens is the light doesn't necessarily get out. If it comes at the right angle, which we're going to identify tomorrow as the critical angle, it will bounce back in. So it gets refracted to such a degree. If it was refracted right along here, it'd be here. Anything more than that is above the critical angle. and it goes down and up and down and up and down and up. That's a pretty important property because that's what makes diamonds expensive. If they bounce around, the light bounces around lots, then they sparkle well. So that cut of that outer surface of the diamond is so important. Diamond cutters get paid a lot of money for a couple of reasons. One is they can ruin a diamond if they cut badly. In a couple of ways, one, they can shatter it, but more importantly, if this angle is not cut well, it can be the same clarity, same size, same number of carats, be worth less if the light doesn't sparkle really well inside. But it's also the phenomena that's used for fiber optics. So when we get to total internal refraction, tomorrow or Thursday, we will talk more about that. So that's the end of this video, folks. I'm going to shut this down and save it, and then I'll start a new one in just a few seconds.